Okay, the final force that we need to think about acting on our material is not just a body force and the surface forces acting over the surface, but also an idea of something that we'll call a line force. As you might imagine from the name of this is something that has a magnitude that is expressed in terms of the force divided by the length of a material line. The most common example of one that we'll see in fluid mechanics is usually given the symbol sigma, and this would be what people would call the surface tension of a material. And the surface tension is, as I said, is usually called sigma. The SI units of it are newtons per meter. But the right way of thinking about it is it's really the energy that's required to make a unit of surface with a given area A. And so if I think about it that way, then I can also think about this as having units of a joule, which is a newton times a meter, divided by meter squared. So in fluid mechanics, we're really interested in the role of forces, so we'll think about it this way as a force. But in material science, you're usually interested in thinking about energies, and so this would be also an example of an interfacial energy density. It's the work that's required to make a certain amount of surface. The values are typically quite small for most materials. So, for example, for water, in equilibrium with air, if we ask what is the value, we've talked about this before, it's 72 times 10 to the minus 3 newtons per meter. So it's a very, very small force, but it can be important on very, very small scales. And so we're going to think about an example to explore this and to see what happens. And a good example to think about is what happens if you're making very, very small channels. So if I'm making very, very small pipes of a radius, let's say that the radius of this pipe is R, and I dip my pipe pipe into water, and it's open at the end, and water is sitting here at equilibrium, and we know that the pressure will increase in the water due to hydrostatics. So the pressure will increase with depth like this. But what you'll find is that in a sufficiently small tube, that actually the water will start to climb up the tube. And so at the end of the day, it will come to rest at an equilibrium position that's higher than the size of the tube. Now, small tubes like this are frequently called either a capillary in American English or a capillary if you're speaking British English. And the idea is that these surface forces and line forces that we're interested in have come to equilibrium in a way where there is a force that's pulling upwards like this, which is set by the shape of the free surface. And so this free surface is often called a meniscus. And the particular height that this will climb will depend on the radius of tube and also the shape of the surface that the liquid takes. So if we were to zoom in on this region, we'd find that locally that the liquid has formed a shape where it has adopted an angle, and this angle is usually called the contact angle theta. And this is a boundary condition that sets the shape of what's going on at the boundary between a solid material and our liquid material. So we have a liquid here, we have a solid here, and so this is an example of a two-phase boundary condition. And this can be important, and we can recognize that therefore line forces are going to be things that at equilibrium they don't really play a role in the material itself or in the liquid itself. They only act at boundaries, and so the line forces typically enter our equations as boundary conditions. So they're not in the governing equations themselves. So if we're going to be using this in a general case, if we take our general domain like this, if I find that it intersects with a boundary, or there's a boundary, then we should expect that everywhere along here, or along this, then we're going to have to apply a boundary condition. And so it now becomes clear why we think about them as line forces, because the magnitude of them is going to depend on the length of the line that intersects with our control volume. We can try and work out exactly how big that is by doing a force balance on this material element. So let's think about the forces that are acting on this material element. Let's denote the height of this by h. And when the system comes to equilibrium, then we'd like to think about what the set of forces are. And so we'll think first of all about the force that's acting downwards. That's a body force. The body force that's acting down is going to be rho times g times the volume of this element. The volume of this element would be pi r squared times h. Okay, so that's a cylinder of material. And it's acting down, and this must be balanced by the force that's pulling up on this. And the force pulling up on this, we can think about it, we can write it as F sigma, and F sigma is going to depend on this, but it's going to be multiplied by the length of the line. So we should expect that this should be something that looks like the length of the line, which is pi r for the circumference with a 2. It's going to depend on sigma, so that's certainly now a force. It's a Newton per meter multiplied by a length. And then since we're doing a vertical force balance, so since we're thinking about the vertical forces, and we're thinking about the sum of the vertical forces, we need to take the component of it that's acting in the vertical direction, and the component of it that's acting in the vertical direction by similar triangles is going to be this component right here. So we'll have additionally a cosine theta there. So we can try and simplify this equation by getting rid of a few terms that are common. And then when I rearrange this, we'll find an expression for the height, which indeed depends on the magnitude of the force, the cosine of the angle, with a 2 in here, and then divided by rho, g, and r. And so you can see that the height that we get it depends completely inversely on the size of the capillary tube. The smaller the radius is, the bigger and bigger this height is. Conversely, the bigger the radius is, the more and more negligible this is. And so if I was to look very, very closely at this, there might be, again, a little angle, a contact angle here where our tube meets this. But that's negligible when we have a big domain. It's only when the domain is very, very small. Two other things that we can note from this. First of all, we can see that it also depends on the cosine of this angle. So the biggest this can possibly be is when the angle is 0. If theta is 0, the cosine is 1, and then the height is as big as possible. So the biggest possible height we could get is when the material completely wets the glass. So in the case that the angle goes to 0, then we would have a force that would look like this. So this would be theta going to 0. We would call that complete wetting. And if my tube happens to be made of glass, then we would say that the liquid likes the glass. And so the word that would be used for that would be hydrophilic. Conversely, when we get to think about surface tension towards the end of this class, we'll see that we might actually have the opposite case. The opposite case would be when the angle approaches not 0, but 180 degrees, in which case the cosine changes sign, and then the material actually won't like this. And so we could have the case where we'll actually have a material that doesn't like to wet the glass. And so inside the tube you'll find that instead that the height is negative and points down. If you've ever seen a mercury, a device for measuring barometric pressure using mercury in glass, you've probably seen an example of this. So for a good example of a material like this is liquid mercury. So just a couple of things that will arise right then. The final thing that we might note about these forces, we've talked about 3 different kinds of forces. So we have body forces, we've had surface forces, and now we've had line forces. And if you go and look at the derivations we've had, we've found that this body force depends on delta V. We've seen that surface forces depend on delta A. And we've seen that line forces depend on the length of the line, delta L, let's say. Now, if we were to think about a little material, a general system like this with a material element of size this, we might say that if we think about this as being the characteristic scale of a length, then the surface, a surface of area A, is something like a length squared. So this will depend on L squared. Similarly, a body force is something like a length cubed, and so this will scale like delta L cubed. And this, of course, is of delta L. And so you can see that what happens as the world gets smaller, as things get smaller and smaller and smaller, line forces get smaller, but surface forces get quadratically smaller, and body forces get cubically smaller. So in general, as the world gets smaller, then these forces will become negligible first. And so the area of microfluidics and nanofluidics is commonly dominated not by gravity, but by interactions between line forces and surface forces. And so much of engineering these days is interested in forces or fluid flow on very, very small scales. And surface tension, therefore, is going to become increasingly important. And we'll return to that at the very end of this class. So we're going to finally look at an example. And so we're going to look at an example that we show here. And this is an example of capillary rise. You can see a tube, a series of tubes of different radii, and you can see that as the radius of each tube gets smaller and smaller, then you can see that, in fact, the height does get larger and larger. The common expression from hydrostatics that we would have, that you might remember as an undergraduate, would be that the pressure down here would be given by atmospheric pressure plus rho g times, let's call it big H. And the same pressure is reached at all points along here, because we know that there's no flow. So we know the pressure has to be the same at every single point. So you can see that the pressure is the same here, and then the pressure must decrease as we go up here, and the final height is given by this expression that we've just derived. So a useful question to ask would be, could you find an expression for the pressure inside the blue fluid just below the free surface at each of these? And how does that depend on the tube radius R?